Welcome back. Let's practice finding gradient vectors. All right, so here's our first example. We want to find the gradient of the function at the given point. And we're given the multivariable function f of xy, which is equal to 4x plus 5y squared plus 1. And the point where we want to find the gradient is the point 1, 2. Okay, so the gradient of a multivariable function of two independent variables is a vector where the x and y components are the first partial derivatives of the multivariable function. It looks like this. The notation for the gradient is an upside down delta, read as del, and so we have the gradient of this function, so del f of xy is equal to the partial derivative with respect to x times I, that is the x component of the vector, and then we have plus fy, the partial derivative with respect to y, times j. That is the y component of the vector. Okay, so let's start by finding this, the general gradient vector for this multivariable function, and then once we have that, we will evaluate it at this point to find the specific gradient vector at that point on the function. And so let's start by calculating fx, the partial derivative with respect to x. So looking at this function here, the derivative of 4x is 4, and then these other two terms are constants with respect to x, so their derivatives are 0. So far, we have 4 times I. 4 is the partial derivative with respect to x of this multivariable function, so that is the x component of the gradient vector, and then we'll have plus fy, which is the partial derivative of the function with respect to y. And so 4x is a constant with respect to y, its derivative would be 0, but then for 5y squared, you do want to use the power rule, multiply that 2 down, and subtract 1 from the exponent, and you'll get 10y to the first power, and then 1 is a constant, so its derivative is 0. So 10y is the partial derivative with respect to y of this function, and that is multiplied by j. It is the y component of the gradient vector. Okay, so this right here, 4i plus 10yj, is the general gradient vector, but we do want to find the specific gradient vector at this point, 1, 2. So let's find that next. We will take our gradient vector and evaluate it at the point 1, 2. And so if we plug in 1 for x and 2 for y, looking at our vector here, there are no x's, so really we don't have to put in 1 anywhere. We just have to worry about plugging in 2 for this y right here. We will get 4 times I plus 10 times 2 j. And 10 times 2 is 20, giving us that the gradient at the point 1, 2 is 4i plus 20 j. And that would be the final answer to this example. Let's take a look at another. Next up, we want to find the gradient of this function at the given point. Our function is z is equal to 2x times e to the power of y divided by x, and the given point is the point 2, 0. All right, so z is defined as a multivariable function of two independent variables. So you could view it as f of xy is equal to 2x times e to the power of y divided by x. And so then from that, you can find the gradient of that function by taking the partial derivative with respect to x and making that the x component of that vector, and then adding that to the partial derivative with respect to y, and that will be the y component. All right, so let's start by finding the partial derivative with respect to x, which will be a little bit more involved this time around. So I'm going to do that work on the side. Let's calculate fx over here. What will that be equal to? Well, in our function, we have a product of two functions in terms of x, right? You have 2x multiplied by e to the power of y divided by x. So because you have two different parts involving x multiplied by each other, you have to use the product rule to find this partial derivative. And so let's use it. We'll take the first function times the derivative of the second. So we have 2x times the derivative of e to the power of y divided by x. The derivative of an exponential function is just that function, but then multiplied by the derivative of its power, or its exponent. So we'll rewrite e to the power of y divided by x, but then you want to multiply by the derivative of y divided by x with respect to x. And y divided by x could be rewritten as y times x to the power of -1. And now you can see how to take the derivative of that. Y is just a constant with respect to x, so just multiply this -1 down, subtract 1 from that exponent, and that will be the derivative. So doing that, you'll get negative y times x to the power of -2. that would be the derivative of y divided by x, which is the power of that exponential function. And so that takes care of the first term of the product rule, right? We took the first function of 2x times the derivative of the second, and then we'll add that to the second function times the derivative of the first. And the derivative of 2x is just 2. So what we get here is plus e to the power of y divided by x times that derivative of 2. Okay, and then simplifying, this will be equal to negative 2xy times 1 divided by x squared times e to the power of y divided by x plus 2 times e to the power of y divided by x. Okay, so all I did here was multiply all these pieces together. So we have negative 2xy, and then this x to the power of negative 2. I moved that to the denominator, so the power is positive, and that's still multiplied by e to the power of y divided by x. Okay, and then of course this term is the same. I just put the 2 out front. Now over here, this x will cancel out with one of these x's. So this x is gone, and this becomes x to the first power. And then notice that these two terms have a common factor of e to the power of y divided by x right here and here. In fact, the common factor is 2 times e to the power of y divided by x. So let's pull that out of each of these terms, and you'll get that fx is equal to 2 times e to the power of y divided by x times negative y divided by x plus 1, right? If you pull 2 times e to the power of y divided by x out of this term, all you're left with is negative y divided by x to the first power, because the 2 and this part are now pulled out. And then for this term, that is everything, so all you're left with is 1. Okay, so that is fx. I would reorder these two terms just to make it look a little bit nicer. And so if you put this into the gradient vector here, this will be equal to 2 times e to the power of y divided by x times 1 minus y divided by x. And that's multiplied by I. Okay, so that is the partial derivative with respect to x. So that's the x component of our gradient vector. Now let's work on the y component, or the partial derivative with respect to y, which is going to be much easier to find because we no longer have to use the product rule. This function only has y in that exponent of e. Okay, we don't have a product of two functions involving y. Okay, so 2x is just a constant multiplied by e to that power. So the partial derivative with respect to y will just be 2x times e to the power of y divided by x, right? You just rewrite the coefficient as well as that exponential part, and then multiply by the derivative of that exponent. And the derivative of y divided by x would just be 1 divided by x, right? Y is to the first power, so its derivative would be its coefficient, which is 1 divided by x. Okay, it's just like if you were taking the derivative of y divided by 2. Okay, the derivative of that would be 1/2. It's the same idea here because we're treating x as a constant. Okay, so the derivative that we're multiplying by is 1 divided by x, and so then those x's will cancel out, just giving you that the partial derivative with respect to y is 2 times e to the power of y divided by x. Okay, so I'll fill that in here. For our gradient vector, we'll have plus 2 times e to the power of y divided by x, and that's multiplied by j. That is the y component of the gradient vector. All right, so that is the general gradient vector, but we do want to find the specific gradient vector for this function at this point 2, 0. So we want to plug in 2 for x and 0 for y into this vector. So let's do that. We will have the gradient of f of 2, 0 is equal to 2 times e to the power of 0 divided by 2, right? Y is 0, x is 2. So we have 2 times e to the power of 0 divided by 2 times 1 minus 0 divided by 2 times I plus 2 times e to the power of 0 divided by 2 times j. All right, now in each case, 0 divided by 2 is 0. So you have e to the power of 0, 1 minus 0, and e to the power of 0, and anything to the power of 0 is 1. So what we get here is that this is equal to 2 times 1 times 1 times I plus 2 times 1 times j. So the gradient vector here at the point 2, 0 is 2i plus 2j. That is the final answer to this example. For our next example, we want to find the gradient of this function at the given point, and our multivariable function this time around is a function of 3 independent variables. We are given f of x, y, z is equal to x times tangent of y plus z, and the given point is 3, 2 pi, negative pi. Okay, so finding the gradient of a function of 3 independent variables is very similar to finding the gradient of a function of 2 independent variables. The only difference is that there is an extra z component for the gradient vector. The formula looks like this. The gradient of f of x, y, z is equal to the partial derivative with respect to x times I plus the partial derivative with respect to y times j plus the partial derivative with respect to z times k. All right, so we're going to go through the same process that we did in the previous two examples, except now we will also find a partial derivative with respect to z for this multivariable function, and that will be the z component of the gradient vector. Okay, so let's work on setting up this gradient vector, and then once we have the general vector, we can plug in the coordinates of this point to find the specific gradient vector at that point for the function. Okay, so let's start with the partial derivative with respect to x. And so looking at this function here, we have x times tangent of y plus z, and tangent of y plus z with respect to x is just a constant. It would just be the coefficient or the number multiplied by x. So if you take the derivative of x to the first power, you're just left with that coefficient. So the gradient will be equal to tangent of y plus z, and that's multiplied by I. That will be the x component. And then let's do the partial with respect to y. Now x would be a constant. It's the coefficient of this tangent function. And y is inside the tangent function. So we do need to take the derivative of tangent now, but then don't forget to multiply by the derivative of the inside function, which in this case would just be 1. You don't really have to worry about that. Y to the first power, the derivative of that is 1, and then z would be a constant with respect to y, so its derivative is 0. So 1 plus 0 is 1. You'll be multiplying by 1 after you take the derivative of tangent. And so the derivative of tangent is secant squared, so we'll have plus x times secant squared of that same inside function, y plus z, and you'd technically be multiplying by 1, but that doesn't change anything, so I'll leave it like that. That is the y component, and would be multiplied by j. Now finally, for the z component, we need a partial derivative with respect to z, which will be very similar. In fact, it will be exactly the same as our partial derivative with respect to y. Because z is inside the tangent function, so we do need to take the derivative of that, but then when you multiply by the derivative of the inside function, it would still be 1. The derivative of y with respect to z is 0, and the derivative of z is 1. 0 plus 1 is 1, and so you'd be multiplying by 1. Okay, so just take the derivative of tangent, and you're good to go. Just make sure to keep that x in the front because it would be a constant with respect to z. So what we get here is plus x times the derivative of tangent, which is secant squared. So we have secant squared of that same inside function, y plus z, and then technically you'd be multiplying by 1, which doesn't change anything, so I'm not going to write that down, but that would be multiplied by k because it is the z component. Okay, and so now we have the general gradient vector, but we do want to find the specific gradient vector for this function at this point 3, 2 pi, negative pi. So let's plug in those values for x, y, and z in this gradient vector. So we will have the gradient of f of 3, 2 pi, negative pi, and that will be equal to tangent of y plus z, where y is 2 pi and z is negative pi. So 2 pi plus negative pi is 2 pi minus pi, and that's multiplied by I. Then you have plus x times secant squared of y plus z. In each case, y plus z is still going to be 2 pi minus pi, but then x is 3. So we have 3 times secant squared of 2 pi minus pi times j. And then the same thing for the z component. It's the same exact expression as the y component. So once again, we get 3 times secant squared of 2 pi minus pi times k. All right, and now simplifying, 2 pi minus pi in each case is just equal to pi. So we have tangent of pi, which is 0. So this is equal to 0 times I plus 3 times secant squared of pi, because 2 pi minus pi is pi, and secant of pi is equal to negative 1. So if you're squaring that, if you have secant squared of pi, then you want to square both sides, and so secant squared of pi is equal to 1. All right, positive 1, not negative 1, even though secant of pi is negative 1 because it is squared the result is positive 1. Okay, so what we get here is 3 times 1 times j, and then you'll get the same thing for the z component because it's the same exact expression. 2 pi minus pi is pi. Secant squared of pi will be positive 1. So we get 3 times 1 times k. So altogether, we don't really need to write the x component because it's 0, but then the y and z components are both 3. So our final answer is that the gradient vector at the point 3, 2 pi negative pi for this multivariable function is 3j plus 3k. That is our final answer. Let's take a look at a slightly different example. For our next example, we want to find the directional derivative at the point 2, 2 in the direction of vector v. And we're given the multivariable function of two independent variables, f of xy is equal to 1 divided by x squared plus y squared, and the given vector v is equal to 2y plus j. Okay, so this is a problem that we have done before in Calculus 3, but we are going to take a different approach this time around. If you watched the lesson video for this topic, then you know that we can find a directional derivative by using the gradient vector, specifically by taking the dot product of the gradient vector with the unit vector that describes a direction in which we want to find the directional derivative. Okay, so here's our goal. We want to find the derivative in the direction of a unit vector for this multivariable function of f of xy, and the way we're going to find it is by taking the dot product between the gradient vector for f of xy with that unit vector, vector u. Okay, so we have to find each of those pieces first before we can find that directional derivative. In fact, we do want to find a specific derivative, so I'll take this one step further. We want to find it at the point 2, 2, which means we can set this up, the derivative in the direction of u for f of 2, 2 will be equal to the gradient of f of 2, 2 dot product with vector u. Okay, so what we want to do here is first find this gradient vector at 2, 2, and then find the unit vector, and then take the dot product of those two vectors. And that will give us the directional derivative that we're looking for here. Okay, so let's start with the gradient vector. Remember that for a multivariable function of two independent variables, the gradient vector for f of xy will be equal to the partial derivative with respect to x times I plus the partial derivative with respect to y times j. And so let's work on finding these two partial derivatives. Starting with fx, we want to take the partial derivative with respect to x of this multivariable function. And it might be easier in this case if we rewrite this function such that we move this quantity from the denominator to the numerator. So I'll do that here. We could rewrite that to be x squared plus y squared to the power of negative 1. Just moving that quantity to the numerator makes that power negative. And now we have an expression that's easier to identify how to take the derivative of. We can use the chain rule here. So I'll start by taking the derivative of the outside function using the power rule. So doing this work on the side, fx is equal to negative x squared plus y squared to the power of negative 2 multiplied by the derivative of the inside function, and the derivative of x squared is 2x, and the derivative of y squared is 0. So you're just multiplying by 2x. Okay, and so I'm going to simplify this, but put it right into my gradient vector. So this will be equal to fx, which will be negative 2x divided by x squared plus y squared squared. And that will be multiplied by I, right? Negative 2x will stay in the numerator, and then I moved this quantity with a negative power to the denominator, so now the power is positive. Okay, and so that's fx, that's the x component of the gradient vector. Now let's work on the y component. Let's find the partial derivative with respect to y, which will actually be very similar. We'll take the derivative of this expression in the same way, but the derivative of the inside function will be different. Okay, we still have to take the derivative using the chain rule because y squared is inside that quantity to the power of negative 1. So for fy, you're still going to have negative x squared plus y squared to the power of negative 2, but then you will be multiplying by 2y. That will be the derivative of that inside function. X squared is now a constant with respect to y, so its derivative is 0, but the derivative of y squared is 2y. All right, so simplifying this and putting it right into the gradient vector, we will have plus negative 2y divided by x squared plus y squared squared. and that's all multiplied by j. Okay, I moved this quantity to the denominator, so we have x squared plus y squared squared. That power is now positive, and in the numerator, you just have negative 2y. So those are the partial derivatives. We have now used them to construct our gradient vector. And so now that we have the general gradient vector, we do want to find the specific gradient vector at this point 2, 2. So let's plug in 2 and 2 for x and y. We'll have the gradient of f of 2, 2 is equal to negative 2 times 2 divided by 2 squared plus 2 squared squared, and that's multiplied by I. And then we have plus negative 2 times 2 divided by 2 squared plus 2 squared squared times j. Now simplifying, negative 2 times 2 is negative 4. 2 squared plus 2 squared is 4 plus 4, which is 8, and 8 squared is 64. So we get negative 4 64ths times I, which is the x component, and then for the y component, it's the exact same calculation, so we get minus 4 divided by 64 times j. Okay, now 4 divided by 64 is the same as 1/16th, and so you can pull that out of these two terms. Specifically, you could pull out negative 1/16th, and so if you do that, you will get a gradient vector of negative 1/16th times I plus j. Okay, so that's the gradient vector at the point 2, 2. We will use that for this dot product calculation, but we can't do it yet because we still need the unit vector u, which will be based on this vector right here that we've been given, vector v. And so don't just dot product this vector right away with the gradient vector. You have to make sure that it either is a unit vector or turn it into a unit vector. And so what you want to do here is calculate the magnitude of that vector. And if it's 1, then you have a unit vector and you're good to go. But if it's not 1, then just divide that vector by its magnitude, and that will give you a unit vector. Okay, so let's calculate the magnitude of that vector. The magnitude of v will be equal to the square root of the sum of its components squared. So you'll have 2 squared plus 1 squared, which is equal to the square root of 4 plus 1, which is 5. So you get a magnitude of the square root of 5, which is not 1. So this vector is not a unit vector, but we can turn it into a unit vector because you can find a unit vector by taking a vector and dividing it by its magnitude. So in this case, our unit vector will be this vector divided by the square root of 5, but I'm just going to keep that on the outside. I'll have 1 divided by the square root of 5 times that vector of 2i plus j. Okay, and the reason I'm going to do that is because when we take the dot product of these two vectors, we can pull out any scalars that we want from either of those vectors and then multiply them by the dot product calculation. Okay, so for the gradient, we can pull out that negative 1/16th, and for the unit vector, we can pull out that 1 divided by the square root of 5, multiply those two scalars together, and then multiply that result by the dot product of I plus j from the gradient vector with 2i plus j from the unit vector. Okay, so here's what that will look like. The directional derivative will be equal to those two constants. So we have negative 1/16th times 1 divided by the square root of 5, all multiplied by the dot product of this vector and this vector. So to take the dot product, remember that you take the sum of the product of corresponding components. So you'll multiply the x components and have 1 times 2, giving you 2. So we have 2 plus the product of the y components. So you'll have 1 times 1, which is 1. So you have 2 plus 1, and that is the result of the dot product between those two vectors. Okay, and that's a whole lot easier than if we were to multiply these scalars through those components, and so that's why I decided to keep them out and just multiply them on the outside. Okay, because then 2 plus 1 is 3, and then you can multiply 3 into the numerator here and get that the directional derivative is negative 3 divided by 16 square roots of 5. And that's it. That really can't be simplified in any way. That is the final answer. It is approximately equal to negative 0.08385. And so that gives you an idea of the actual value of that slope. But this is the slope or the directional derivative at this point on this surface in the direction of this vector. Let's take a look at another example. Hey, real quick, before we take a look at the next example, if you find my videos here at JK Math to be helpful, then I'd like to invite you to join my membership site JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out, as it's a great way to support me in the tutorials I make, as well as a great way for you to learn math better. But for now, let's take a look at the next example. Next up, we want to find the directional derivative at point P1 with coordinates of 4, 2, 4 in the direction of point P2 with coordinates of 8, 0, 8. And we're given a multivariable function with 3 independent variables, f of x, y, z, and it's equal to the square root of x times y times z. Okay, so just like in the previous example, we want to find a directional derivative, and we will do that with the help of a gradient vector. But do notice that our multivariable function has 3 independent variables, so that gradient vector will look a little bit different. It's going to have an extra term, or z component, that is based on the partial derivative of this function with respect to z, that third independent variable. But also, notice that the way that we are given the direction for this directional derivative is a little bit different as well. Instead of being given a vector, we've been given 2 points. And if you've done a lot of practice finding directional derivatives, then you've probably seen this before. But what we will end up doing here is finding a vector between these 2 points, and that vector will have the direction that we need for the directional derivative. Okay, but let's just do one thing at a time here. The goal that we are working towards is to find a directional derivative, or the derivative in the direction of a unit vector u, for this multivariable function, f of x, y, z, and that will be equal to the dot product of the gradient vector for f of x, y, z with the unit vector u. Okay? And specifically, we want to find the directional derivative at this point P1 with coordinates of 4, 2, 4. So really what we want to find here is the derivative in the direction of u of f of 4, 2, 4, which will be equal to the gradient of f of 4, 2, 4 dot product with the unit vector u. Okay, so what I want to do first is find this gradient vector. And so how would we find that? Well, the gradient of f of x, y, z will be equal to the partial derivative with respect to x times I plus the partial derivative with respect to y times j plus the partial derivative with respect to z times k. Okay, so we have to find these 3 partial derivatives of this multivariable function in order to set up this gradient vector. Okay, and so let's work on each of those one at a time. Let's start with fx, the partial derivative with respect to x. And looking at our function here, x is inside this square root function, so we will want to use the chain rule here. And to help us use that, I'm going to rewrite the function as x times y times z to the 1/2 power. And then since x is inside that quantity, we need to use the chain rule. We'll take the derivative of the outside function and multiply by the derivative of the inside function. So using the power rule, we will get 1/2 times x times y times z to the negative 1/2 power, and then that will be multiplied by the derivative of that inside function, which will just be y times z, right? X is to the first power, so its derivative is its coefficient, or the number being multiplied by it, which will be y times z. Okay, so we multiply by y times z. That would complete our partial derivative with respect to x, and we can simplify that later, but I want to first find the partial derivatives with respect to y and z, which are actually very similar to this partial derivative, because y and z are also inside that square root function. So in each case we're going to use the chain rule. The only thing that's going to be different is the derivative of the inside function. All right, for fy, you will still have 1/2 times x times y times z to the negative 1/2 power, but then you'll be multiplying by the derivative of that inside function with respect to y, which will be x times z. The derivative of y to the first power is just going to be its coefficient, which would be those 2 constants of x and z, at least with respect to y. So we'd be multiplying by xz, and then again, a very similar process for fz. Z is inside that square root function, so you're still going to take the derivative using the chain rule. You'll have 1/2 times x times y times z to the negative 1/2 power, but then you'll be multiplying by the derivative of the inside function with respect to z, and z is to the first power, so its derivative would just be the coefficient of x and y. X and y are constants with respect to z, and so they will be the coefficient. So we'll multiply by x times y. Okay, so those are the partial derivatives with respect to x, y, and z. And so now we can set up our gradient vector. It will look like this. Fx, if we rewrite it to look a little bit nicer, I'll keep yz in the numerator, but then move this quantity to the denominator so that power is positive, and then just rewrite it as a square root function. It'll be in the denominator with this 2, so you'll have yz divided by 2 times the square root of x, yz, and that will be multiplied by I. Then you'll add that to fy, which in a very similar manner to fx, we can move that xz in the numerator, move this quantity to the denominator, rewrite it as a square root, and altogether you'll have x times z divided by 2 square roots of x times y times z, and that's all multiplied by j, and then you'll add that to fz, which can be simplified as well. xy will be in the numerator, and then move this quantity to the denominator and rewrite it as a square root. So we get x times y divided by 2 square roots of x times y times z, and that's multiplied by k. All right, and so now we have our gradient vector, at least the general gradient vector, in terms of x, y, and z, but we do want to find the specific gradient vector at the point where we want to find the directional derivative, that 0.424. So we want to plug in 4 for x, 2 for y, and 4 for z in this vector. So here's what that will look like. We'll have the gradient of f of 4, 2, 4 is equal to y times z, so 2 times 4, which is 8, divided by 2 times the square root of x times y times z. So you'll have 4 times 2 times 4. So we get the square root of 32. That will be the same thing for each of these square roots of x times y times z in those denominators. And so that's multiplied by I, but then we'll have x times z, which is 4 times 4. That's 16. So you have 16 divided by 2 times the square root of 32 times j. And then for the z component, x times y is 4 times 2, which is 8. So you have 8 divided by 2 square roots of 32 times k. All right, and then in each case, 8, 16, and 8 can all be divided by 2. And the square root of 32 can be simplified because it has a factor that is a perfect square. You could rewrite the square root of 32 as the square root of 16 times 2, and the square root of 16 is 4. So this would be equal to 4 square roots of 2. And so here's what you'll get. This is equal to 8 divided by 2 times 4 square roots of 2 times I, plus 16 divided by 2 times 4 square roots of 2 times j, plus 8 divided by 2 times 4 square roots of 2 times k. 2 times 4 is 8, so you have 8 divided by 8, which is just 1. So these will cancel out. And then 16 divided by 2 times 4 is 16 divided by 8, which is 2. So this is gone, and this will just become 2. And then 2 times 4 is 8. 8 divided by 8 is 1, so those cancel each other out as well. So what we get for this gradient vector is 1 divided by the square root of 2 times I, plus 2 divided by the square root of 2 times j, plus 1 divided by the square root of 2 times k. All right, and then to make things simpler later, when we do this dot product, I am going to pull out a common factor from these 3 components, that being 1 divided by the square root of 2. You can pull it out of all 3 of these components. So here's what that looks like. Our gradient vector will be 1 divided by the square root of 2 times 1i plus 2j plus 1k. All right, and so that is the gradient vector at the point 424, which is half of what we need to find this directional derivative. Now all we need is the unit vector. And to find the unit vector, we first need to find a vector between these 2 points. That will give us a vector that has the direction from this point to this point. And to find a vector between 2 points, what you need to do is take the coordinates of the terminal point and subtract the coordinates of the initial point. So that will look like this. Vector v will be equal to 8 minus 4 times I plus 0 minus 2 times j plus 8 minus 4 times k. All right, the x component is 8 minus 4. You subtract this x coordinate from this one. The y component is 0 minus 2. You're subtracting this y coordinate from this y coordinate. And then the z component is 8 minus 4, which is this 8 minus this 4. You're subtracting this z coordinate from this z coordinate. Okay, so simplifying, v is equal to 4i minus 2j plus 4k. And so now we have a vector between those 2 points that will have the direction that we need for our directional derivative, but it does need to be a unit vector. So let's check that next. We need to know what the magnitude of this vector is. If it's 1, then we're good to go. But if it's not, then we need to divide that vector by its magnitude. Okay, so the magnitude of vector v will be equal to the square root of the sum of its components squared. So we have 4 squared plus negative 2 squared plus 4 squared. 4 squared is 16, negative 2 squared is 4, and 4 squared is 16. So we get 16 plus 4, which is 20, plus 16, which is 36. So this is equal to the square root of 36, which is 6, and that's not a magnitude of 1. So this vector was not a unit vector, but we can turn it into 1 by dividing it by 6, its magnitude. Okay, and so here's how I'm going to express that. The unit vector will be equal to vector v divided by its magnitude, which will be equal to these components divided by 6. But I'm just going to keep that 6 on the outside, specifically 1/6, because we would be dividing all these terms by 6. So you could pull out a 1/6, and it would look like this. You'd have 1/6 times 4i minus 2j plus 4k. All right, and the reason I'm doing that is because it's going to be easier to work with these components without that 1/6 in them, just like it's going to be easier to work with these components without the 1 divided by the square root of 2 when we use these vectors for a dot product. Okay, because one of the properties of the dot product is that we can pull out any scalar multiples from our two vectors and just multiply that by the result of the dot product using the components without those scalar multiples. Okay, so now we have both the gradient vector and the unit vector, so we can now take a dot product between those two vectors to get the directional derivative that we want for this problem. And so we'll set that up here. I'm going to first pull out those two constants, or those scalar values, and multiply them by one another. We'll have 1 divided by the square root of 2 times 1 divided by 6, and then that will be multiplied by the dot product of those two vectors without those scalar multiples. All right, so we'll take the sum of the product of corresponding components. So we'll start by multiplying the x components. We'll have 4 times 1, which gives you 4, plus the product of the y components. So we have negative 2 times 2, which is negative 4. And then we have plus the product of the z components, which will be 4 times 1, which is 4. So we have plus 4, and that is the dot product calculation. And then inside, negative 4 and 4 cancel out to become 0. So you just have 4 multiplied by this expression, giving you 4 divided by 6 square roots of 2, which can be reduced because 4 divided by 6 would reduce to 2/3. And so you get 2/3 times the square root of 2. That right there is the directional derivative at this point on this surface in the direction of this other point, or in the direction of this unit vector that gives us the direction from this point to this point. Okay, and so if you wanted the approximate value here, to get an idea of the actual value of that slope, 2 divided by 3 square roots of 2 is approximately 0.4714 and some more decimals. Okay, but with that, that is it for this example. And so let's move on to a slightly different one. For our next example, we want to find the maximum and minimum value of the directional derivative at the given point. And we have a multivariable function of two independent variables, f of xy, which is equal to x squared plus 2xy, and the given point is 1, 0. Okay, so to find the maximum and minimum values of a directional derivative, you have to be familiar with the properties of the gradient vector. Two of those properties being that the magnitude of the gradient vector is the maximum value of the directional derivative, and the negative magnitude of the gradient vector will be the minimum value of the directional derivative. Okay, if you want more details on why that is the case or where that comes from, be sure to watch my lesson video for this topic if you haven't already, because in this video our focus is going to be on the calculations, although I will do a little bit of explaining after we get the answers. But what we have to do here is first find the gradient vector for this multivariable function, because once we have that gradient vector, we can find the specific vector at this point and then take the magnitude of that gradient vector, and we'll be able to find the maximum and minimum values for the directional derivative. Okay, so in this case, we have a function of two independent variables. So the gradient vector will look like this. The gradient for this function, f of x, y, will be equal to the partial derivative with respect to x times I plus the partial derivative with respect to y times j. Okay, and so let's start with the partial derivative with respect to x. Looking at our function here, the first term, the derivative of that with respect to x would be 2x, and then for the second term here, x is to the first power, so its derivative would be its coefficient, or the number multiplied by it, which would be 2y. We'd be treating y as a constant in this case. All right, so the gradient vector is equal to 2x plus 2y, that's the x component, so it's multiplied by I. And then for the y component, which is the partial derivative with respect to y, the first term would be 0 because x squared would be a constant with respect to y. Its derivative is 0. And then for 2xy, y is to the first power, so its derivative would be 2x, the coefficient of that variable. So fy is 2x, and that is multiplied by j. All right, so that is the general gradient vector, but we want the specific gradient vector at this point 1, 0. So let's plug 1 in for x and 0 in for y. We will have the gradient of f of 1, 0 is equal to 2 times 1 plus 2 times 0 times I plus 2 times 1 j. And so simplifying, 2 times 1 is 2, 2 times 0 is 0, so 2 plus 0 is 2. So the x component is 2, giving us 2i, and then of course 2 times 1 is 2, so we get 2i plus 2j. That is the gradient vector at 1, 0 for this function, and now that we have that, we can calculate the maximum and minimum values of the directional derivative for this multivariable function at this point. All right, all we have to do is take the magnitude of this gradient vector. Okay, so the maximum is equal to the magnitude of the gradient vector, so the gradient of f of 1, 0. And so let's calculate that. That will be equal to the square root of the sum of the components squared. So we'll have 2 squared plus 2 squared, right? 2 squared plus 2 squared. 2 squared is 4, so you have 4 plus 4, which is 8. So it's equal to the square root of 8, which could be simplified to be 2 square roots of 2. Right, you would have the square root of 4 times 2, and the square root of 4 is 2. So the square root of 8 is equal to 2 square roots of 2. That would be the maximum value of the directional derivative at this point, or you could think of it as the maximum or steepest slope for that function at this point. And then the minimum value would just be the opposite, because the minimum value is the negative magnitude of the gradient vector. Okay, so we don't have to do that calculation again, unless we think we did it wrong, which we didn't. It is 2 square roots of 2, so the minimum value will be negative 2 square roots of 2. That is the minimum value of the directional derivative at this point on the function. Okay, and again, if you want the full context surrounding why this is the case, why this works, and why it makes sense, please do check out my lesson video on gradient vectors. Okay, let's move on to the last example for this video. All right, so for our last example, we want to find the maximum and minimum value of the directional derivative at the given point. And we're given a multivariable function of 3 independent variables, f of x, y, z, is equal to x times y squared times z squared, and the point 2, 1, 1. Okay, so this is just like the previous example, except now we're working with a multivariable function of 3 independent variables as opposed to 2 independent variables. But really, our work is not going to be all that different. The only thing that's going to change is that our gradient vector is going to have an extra component where we will need to take a partial derivative of this function with respect to z, the third independent variable, but everything else is the same. We'll need the gradient vector for this function. We'll then evaluate it at this point, and then we'll take the magnitude of that gradient vector. The positive magnitude is the maximum value of the directional derivative, and the negative magnitude is the minimum value of the directional derivative. Okay, so let's find the gradient vector for a function of 3 independent variables. The gradient of that function, f of x, y, z, will be equal to the partial derivative with respect to x times I plus the partial derivative with respect to y times j plus the partial derivative with respect to z times k. All right, and so let's find each of these partial derivatives, starting with fx. Let's take the partial derivative with respect to x of this function. And x is to the first power, so its derivative will just be its coefficient, or the number multiplied by it, which will be y squared times z squared. So our x component is y squared times z squared, and that will be multiplied by I. And then we'll add the partial derivative with respect to y, and so x and z squared will now be constants, so leave them alone, and take the derivative of y squared using the power rule, multiply that 2 down, subtract 1 from the exponent, and you'll get 2x times y to the first power times z squared, and that will be multiplied by j. And then finally, for the z component, we need the partial derivative with respect to z, so now x and y will be constants, so take the derivative of z squared, leaving these constants alone, multiply that 2 down, subtract 1 from the exponent, and you'll get 2x times y squared times z to the first power. And that is the z component, so we'll multiply it by k. And so that's the general gradient vector, but we do need to evaluate it at this specific point before we can find the maximum or minimum values of the directional derivative. So let's plug in 2 for x, 1 for y, and 1 for z. We will get that the gradient vector for f of 2, 1, 1 is equal to 1 squared times 1 squared times I plus 2 times 1 times 1 squared times j plus 2 times 2 times 1 squared times 1 times k. Okay, I replaced all the x's with 2, all the y's with 1, and all the z's with 1 as well. And so simplifying, 1 squared is 1 times 1 squared is still 1, so we get I plus 2 times 2, which is 4, times 1 squared, which is still 4. So we have I plus 4j, and then for the z component, 2 times 2 is 4, times 1 squared is still 4, times 1 is still 4, so we have plus 4k. All right, so that is the gradient vector at this point for this function. Now, to find the maximum and minimum values, we need to take the magnitude of this gradient. So let's do that here. The magnitude of the gradient of f of 2, 1, 1 will be equal to the square root of the sum of the components squared. So we'll have 1 squared plus 4 squared plus 4 squared. 4 squared is 16, plus another 4 squared will give you 16 plus 16, which is 32, plus 1 squared, which is just 1. So you'll get 1 plus 32, which is 33, giving you the square root of 33. So the max value of the directional derivative will be the positive square root of 33, and the minimum value of the directional derivative will be the negative square root of 33. Okay, that would be my final answer to this example. The maximum value is always the positive magnitude of the gradient vector, and the minimum value is always the negative magnitude of the gradient vector. And so with that, we have completed this example, and this was also the last example for this video. But if you do want to get some additional practice, I have another example available on my membership site. And so if that's something that interests you, feel free to look into becoming a member. You can find all the details on my website at jkmathematics.com/plus. If you have any questions, please let me know in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.